So in this course till now, we've seen how the microscopes work, particularly the transmission electron microscopes. We've seen a demonstration on a lanthanum hexaboride filament TEM, which is the JEOL 2100. Then we've seen a conventional cold fed TEM, which does not have any image corrector, the JEOL F200 microscope. We've seen the operation in various modes of the microscope. And we are now with the JEOL NeoARM aberration corrected microscope. So in this instrument, we actually have something called as the image corrector. Let us try to understand how this microscope functions. We've already seen some concepts on what aberrations are, how the aberration is considered as a polynomial function, and how we start correcting the aberrations by using the Zemlin Tableau and the automated software. So we will look at the practical aspects of this in this particular demonstration. We'll first look at the image corrected TEM, and then we'll also look at the probe corrected TEM, look at the various components, the operational modes, and how is this useful to achieve or break the sub-angstrom barrier in achieving very good resolution. What you see here is a cold fed TEM. So on the top here, you have the field emission gun. This is exactly the same kind of a field emitter that you saw on the F200 microscope as well. So by the electron tunneling, at low temperatures, we have the emission of electrons and we form a very coherent probe. And as we go down, we have series of condenser lenses here. This instrument has all automated apertures. If you can come closer, I'll show you where the apertures are. So these are all the motorized apertures, and the layout is of course the same as you have in any transmission electron microscope. You have the FEG on the top, the condenser lenses. Here is where your specimen goes in. So the goniometer is here. You insert the specimen holder here. So as you can see, below the goniometer is where your aberration corrector is. It is called as the set core system in this. The aberration corrector here is on the objective lens, and this is for obtaining spherical aberration-free images in this microscope. What you have here is essentially series of hexapole lenses, and you also have a transfer lens and another hexapole lens. And essentially, as we've seen in the lectures on aberration, you are introducing negative CS with the aberration corrector. So the idea is, in this microscope, the objective lens introduces positive CS, the aberration corrector introduces a negative CS, and collectively you're lowering the CS of the condenser objective lens system depending on where you're placing the corrector. If the same kind of a corrector is placed before the goniometer and just after the illumination system, you call it as the probe corrector. And right below the corrector, you have the illumination system and all the lenses. And what you see here is actually a biprism. So this biprism in this particular instrument is actually a platinum wire. You can displace this in X and Y directions and move it inward. And you can apply a potential on this platinum wire. And when you do this, you obtain interference patterns or fringe patterns, which are called as holograms. So in this particular instrument, you can obtain sort of spherical aberration free or spherical aberration minimized images in combination with phase images from electron holography. And if I go down here, this is where your detection system is. You cannot see it, it is all concealed, but if we come to the side, somewhere in this location, below the microscope column, you have a camera. In this particular microscope, we have the Gatan Rio camera. We'll look at various components of the microscope again, and we'll start looking at the interface and the layout of the control console, and we'll understand how to start operating this instrument very shortly. So if we move on, so if we look at the layout of this instrument, what we see here is the high tension tank. This is the 200 kilovolt high tension tank for a JEOL system. And you can see the cable here goes towards the electron source, that is the cold field emission gun here. And this cable is for the grounding. And what you see here is essentially the water flow controller. This microscope actually aims at obtaining sub-angstrom resolution, and it is imperative that you ensure that all of these components are running properly. These are usually fine, but it is always a good practice to check if everything is fine, the levels of the water flow controller are at the right levels periodically. If we move further on to the other side of the instrument, so over here you have the biprism controller. This is essentially a power supply to apply a potential on the platinum wire in the biprism holder that you saw some time ago. And then we have the card console here. So usually there are several electronic cards which are controlling either your corrector or the instrument, various scan coils and so on. And this is not something that we frequently look at, but sometimes we turn off and turn it on again when there are some errors in the system. So here is the water flow controller for the image corrector, and here is the power supply for the image corrector. This also has a control PC inside this to run the program for image correction. It is important that you check if this particular power supply is switched on, and when I show you the software demonstration, you should ensure that all these connections are established so that the aberration correction system is running fine. Most of the times when you run into problems, you either see that there is an issue with chilled water supply, or there is an issue at the chiller, or maybe the power supply is off. So just ensure that all of these are on. And if you come closer onto the console here, so when you check out this power supply system here, typically all of these LEDs should be green, and this input-output LED should be glowing in amber and green. This is normally a healthy state of this one. In case there is an error, a red LED glows off or this amber LED stops flashing here. So that's an indication that you have to reset and restart this power supply for the at-core control system. We'll move further behind and see the locations of the chiller and the power console. So if you check here, this is the chiller for the aberration corrected TEM system, the image corrected system. Ensure that the output temperature is at the set value. The set value is 17.5, but what we read here is 17.9, and the control temperature is 18 degrees, and these LEDs should be green. Occasionally you might see an alarm here and you have to reset the system here, or sometimes if there are some power issues, this may turn off. What you have here are two power supply consoles, and on this power supply console you actually see the readings of the sputter ion pumps. So in this particular microscope we have several sputter ion pumps, and two of them, the readings are actually red here. If everything is green here and it is running and these dials are indicating the pressures at the optimum values, things are running fine. Occasionally when you run into issues with rebooting the microscope system or resetting some of these power supplies, it comes in handy to know how these objects or how these components look like, and you can usually come down here. This is just to give you an idea of how these accessories to run the aberration corrected TEM look like, and it is not essential that you always reset something unless it is necessary. Let your facility manager take care that all these components are running as required and the instrument is in good health. But just in case there is some issue, to know where to troubleshoot and to diagnose, I'm showing you a layout of the system. How the software console and the control pad of the microscope is, and we'll go to the instrument console now. Let's go there. Here is the instrument console, the main joysticks or the control pads or however you call them. And in this particular instrument, we have mainly three PCs. One of the PCs is actually right next to this console here, the TEM PC, on which all the software to run the microscope is. So this is the TEM center on which we actually control the microscope, and connected to the TEM PC only is the JEOL Cytex software. This actually helps you record whatever you see on the fluorescent screen camera. If you have noticed on this particular microscope, you do not have a fluorescent screen camera or a binoculars to look at the fluorescent screen. It is kind of remotely operable. So you have a camera which is looking at the fluorescent screen, which is below the projection lenses. And on this particular monitor, what you see is the Gatan digital micrograph software. There is the Gatan PC to control the camera. And apart from these, there's another PC which I showed you in the set core control panel. That is where your aberration corrector PC is. So typical procedure is you ensure that all the PCs are running and the user layout is all looking proper, and then you can start imaging on the microscope. We'll now understand the softwares that are typically used and what is the usual layout and when is it good to actually load the holder into the microscope, and we'll look at some basic imaging and obtain some high resolution images on this TEM. So like I was mentioning, the first software that you see is the TEM Center, which looks with this, which is this blue hexagon that you see here. Please ensure that once you come to the instrument, on the bottom right taskbar here, this TEM server should be connected and should be running. If you look at this icon here, there is this thing which is turning in circles, and this is an indication that your TEM server connection is established and it is running proper. Sometimes many problems actually come when this connection is not proper, and you may have to restart the PC or reset the panel on the microscope. So I'll show you the TEM Center software, and then the SciTex software is here, where it is a replacement for the fluorescent screen or viewing directly into the binocular. And then one of the other important softwares here is this particular one, which is the ATCore service. I've loaded a pre-alignment already, and through this software you actually control the image corrector. What is very important once you turn on this software is ensure that these four icons that you see here, the ones which are written as to EM, from EM, supply and image, these are all checked and are in green. If there is an error here, this actually turns into red and you may have to reset or restart the corrector PC. There is a software restart to do this. Usually if you run into an error, you go to this window here and you can say reboot the corrector PC, and it reboots this whole thing. Now because the corrector is in a healthy state, we'll not go there, but this is just to give you information on when you're requested to reboot corrector PC. First thing is you try to reboot it remotely. If this doesn't work, you can then go physically to the ATCore power supply panel, and then you can reboot the PC from there. And then the next software is Gatan digital micrograph, which is shown here. You go here and then you choose the TEM imaging, and this is to control and capture the images that are recorded on the microscope. Now we'll go to the main console and the main TEM PC and understand the layout of what information you have here, and we'll also look at the control pads and understand how to operate the microscope. So in order to start using the microscope, let me show you how the layout of the control panel is. As you can see, there are two control panels, one onto the left and one onto the right, and you have the stage control here. On this you have the X tilt and Y tilt buttons here. So this is to tilt your specimen holder. This is to adjust the height of the specimen holder. So when you do eccentric correction, you use this button here. And on this you have this trackball. This is essentially to displace the holder in X and Y directions. You can also apply small shifts here. When you select this super fine, you can actually go into the piezo mode. You can activate the piezo mode, and here the coarse mode is now selected. So these both are essentially for controlling the holder, that is for tilting and for displacing the specimen position. And if I now start looking at the control pad on the left, you see here all the aperture controllers are over here. On this microscope there are several apertures. all motorized apertures, and I can choose, for example, if I select this, now it shows CL1 open, and if I select this one, I insert the first CL1 aperture, which is 150 micron. If I click open here, it retracts all the apertures. So likewise, I can choose whether it is CL1, CL2, the upper objective lens aperture or the lower objective aperture, the selected area aperture, and so on. This is mainly for aperture control. And here you can see this is to displace the aperture either in X and Y directions. And when I select coarse here, this is essentially increasing the amplitude of the displacement. So if I want to move the apertures over large distances, I select coarse here. This one is essentially sort of your illumination control. You can select the convergence angle here. There are different alpha values that you can change. So when I change this alpha selector, I can go from either alpha 1, 2 or 3, where I change the convergence angle. This is to select the spot size of the beam that I'm actually using. And this is to switch between the TEM mode or the probe mode. Depending on what kind of analysis you do, whether you require a probe or a broad beam parallel illumination, you need this. Now here is, once you switch on the emission, this is sort of the beam control valve. So you press this, your column valves are actually opened when I press this. Here you have all the alignment knobs. You have the PL alignment knob here. You have the image shift. This is for objective stigmation, coarse corrector setting, stigmation, condenser stigmation, and beam align. And when I select any of these, the X and Y deflection knobs get activated. So depending on whichever operation I want to do, I can select that. So for example, if it is just beam align, I can see that the blue LEDs here have glown, and this coarse now makes it displays over larger amplitudes. Here you have the shift X and shift Y knobs. This is to move your electron beam in X and Y plane, which you see on the fluorescent screen. This one is to actually lift the screen. So when I press this, you can hear a noise in the background. The screen is lifted. And here, this is for the image wobbler. These are sort of function knobs here, F1 to F6. Each knob has a different setting. For example, F1 is to go to the ronchogram. F2 is for spot alignment on this microscope. F3 is anode wobbler. F4 is gun alignment. And then F5 is beam stopper. And F6 is for scan mode. So when you do this in STEM mode, you can actually choose some of these. And the knobs F3 to F6 or F5 are for gun alignment. Depending on what is required, you can always use these knobs. Now, over here, you can see you can switch between different magnification modes. You have the mag mode, the low mag mode, the SA mag mode, the diffraction mode, and also the PS mag mode. So depending on how you are choosing the range of magnification that you want, whether you are in a low mag mode or in Lawrence mode, for example, on this instrument, to switch to Lawrence mode, I can just go to this low mag and change the magnification here. And there is a set of calibration values for the lens currents based on which you can use it in Lawrence mode as well. The next important buttons here is this mag selector, where you can toggle this to the left or right. You can switch from magnifications as it is currently 50,000x. So you can go on to different levels of magnification. This one is for diffraction focus. Unlike on the F200 microscope, you have two separate knobs here, one for objective focus and one for diffraction focus. The standard focus, once you load your saved alignment files, you typically press this to run a loop, and then you see that all the lens currents are at the standard preset values as per the previous working alignment. These two knobs here, when you're recording STEM images, you're scanning, and this is to set the brightness and the contrast of your STEM images. So this is the overall layout of the microscope control pads, and I will just refer to what I'm doing when I show the recording on the software, and we'll go through the software layout as well once, and we will see how to operate this instrument after loading the holder. So now we'll move on to load the specimen holder. The sample we are going to study today is actually a standard gold cross-grating specimen. I'll only show you some basic imaging modes and basic correction operations with the Corrector software. So here is a standard double tilt low background holder, and I'm now loading this into the goniometer here. This microscope does not have the spec porter for now. So this simply has to be loaded. Connect the tilt-Y cable here. The tilt-Y motor cable is connected. And after I put this in, I heard some kind of a clicking sound. Once I hear that, I lift this up and I start pumping. So once I start pumping, the amber LED goes off here. I have to wait. This is similar to how it is on the 2100 TEM. I should wait till the green LED goes on, and then the step that I do first is I turn the holder in clockwise direction by approximately 15 degrees. It goes in by one step, and then I turn it again further by 75 degrees. And while it is being turned towards 75 degrees, I have to hold the holder carefully, because now it is actually pumping in the airlock chamber here. So the holder is resting here on the first O-ring, and it is getting evacuated around the first O-ring right now. And once it shows that it is holder ready, once it goes in, as the column is under ultra high vacuum, there's a good chance that the holder gets pulled in. So please be very careful that you hold this and the holder doesn't crash in into the microscope. The risk, if it does crash in, is you might actually hit the pole piece or something in between, and you can cause irreparable damage. So please be careful with this. The green LED is on now. So like I was mentioning, we turn this by 15 degrees. The amber LED is off, so the pumping has stopped. And I turn it further by 75 degrees more, and I'm holding the holder tight so that it goes in slowly. I can close this, and in order to avoid any acoustic interference, it is always a good practice to close this holder cover. But sometimes when you have some special in situ holders, it is difficult to close this cover. The holder is now loaded into the microscope column, and we can start operating the software and start obtaining some images. Let's check the imaging now. So now that the holder is loaded in the microscope column, we'll look at the software and see how the instrument is operated. I've shown you the layout of the control pads. You might not be able to see this directly, but let us start seeing how I operate the microscope, and I'll give you an overview of the software layout and the important components that you need to pay attention here. The first thing that you need to check on the TEM PC again is ensure that this TEM server is running, and the software that we use to control the microscope is the TEM center. So this blue hexagon icon is the TEM center, and this X icon is the site X on which you see the fluorescent camera. So if I look at the overview of the software now, there is a lot of information in this left column that you see here. On the top, you can choose whether you are operating in TEM mode or in STEM mode. Here you have the high tension. If I click on this window pops up. This green color on this 200 is on, and you can see that the status shows HT on. So normally if the high tension is off, you turn it on and then it automatically starts running the high voltage at a safe rate such that it reaches the desired high tension value. Right now it is on, and the first step that we usually do is you turn on the emission. On this microscope, you have a cold field emitter, and you need not do manual flashing of the filament before turning on the emission here. So if I click on auto emission on, you get this warning, are you sure you want to turn on emission after flash? So each time I actually run this, it starts this flashing and then it starts on the emission. And on this particular instruments, the NeoARM microscopes, what is important is once I start flashing and emission, The emission current now, it is turning on, and this value reaches approximately around 15 microamp. The JEOL factory setting is such that this emission current drops by about 25% over a period of 1 hour. So this is usually considered as a standard value, but if your emission current drops significantly lower than say 10 or 8 microamperes, you might have to switch off the emission and turn on the emission again. This is one of the drawbacks of the cold field emitter. I wouldn't really call it as a drawback, but in comparison with the Schottky FEG and the thermal FEG, the emission currents are not sustained at a steady value over a very long period of time. But nonetheless, if your emission currents are good enough to get some good imaging, that is already good enough, and the coherence is really good. So now the status is operational. So I can now turn on the beam by either clicking this, or I go onto the control panel and then I click beam on. So once I click beam on, let us switch to the screen where the Cytex camera is shown, the Cytex software is shown, and I will lower the magnification. I see something on the screen. Let me spread the intensity knob, and it appears like the gold cross-grating sample which is loaded is sort of blocking the path of the electron beam. So let me move the stage, and as you can see, if I spread the beam, right now no aperture is inserted, and this is my gold cross-grating sample. So this is sort of a continuous film, and let me spread the beam fully, and so when I converge the beam, you see the object or the image that I record on the camera is moving. This indicates that the specimen is not at the right height. So what I do is I click on CL1 button, and it is in open state now, and I insert the CL1 aperture. So you see the CL1 aperture is now inserted, and if I click on the brightness button here, the amplitude at which the brightness or the intensity is changing is varying. I see the beam is not centered. I'll just use beam shift knob to center the beam to the screen, and just as a guideline, I will show this reticle here, this circle here. So I'll just center the beam with respect to this crosshair markers that are there, and I spread the beam out. So like in any standard microscope operation, once I load into the TEM, the first step is bringing this to the right height. And to do this, I have to go to a magnification of around 50,000x, and I press the standard focus a couple of times, and I can start changing the height either by pressing the Z plus or the Z minus, or I can simply go to this holder on this column here. If I click on the one of this holder or XY, I get this stage controller button here, and I can actually correct the height by setting Z 10 micron for example, and then changing it in steps here. You can see that when I go in Z minus direction, the contrast is not changing significantly, so I'll just go in Z plus direction. So the Z height now is at around approximately around this, let us say around minus 73 micron. I see the contrast is minimum. So here is where your specimen is at the eucentric height, and from here we can start doing some basic alignments. I'll now go through the software once again, just show you what all information you have here. So you have the beam condition or the high tension value here. This is where we switched on the emission. The vacuum information is shown here. So when I click on vacuum, this window pops up, and you should be sure that before I insert the holder, all of these values, pig 6, 5, pig 4, pig 3, pig 5, pig 6, and pig 1, which is the column, detector chamber, the RT and the pipe values are all evac ready, and the specimen chamber is usually not ready. After you insert the holder, and if you can switch on the wall, this shows ready actually. And then if I go to the left side of the software again, you have the information about the illumination system. You know which mode you are here. You can choose these from the control pad or from the software itself. The alpha value is TEM-S now. Spot size is 1. The specimen information here is here, and the image forming system information is here. All your magnification values, the defocus, and whether you're using superfine, neutral, standard focus, which is connected to the focusing, is all given here. The wobbler controller is here. You either need it sometimes or you don't need it. And the specimen holder information is here. We inserted the reinforced specimen tilting holder, so that was already selected. And this shows your nanospace map. If I want to store a location of the specimen, I can choose this. If I identify an interesting region in the specimen, I can identify it here. And the stage controller is here. We use this to move the specimen stage in up and down direction. So that is by changing Z plus and Z minus. This is how we brought it to the eccentric height. And this is another important information here. You see that all the lens or deflector monitoring system is given here. When I change the objective focus, for example, I now press coarse focus here. When I turn the knob, you can see on the screen the focus changes significantly, but you should also notice that the OL value changes here. When I press standard focus, you see that it reaches a preset value of 6.82 volt, and this is actually close to your eccentric height. I'll briefly correct this to bring it to the right height. And one common practice, if your facility is maintained regularly and the maintenances are done periodically, you can actually go here to this control page and click on alignment panel, and this actually loads here. This window is shown, pops up, and you can load the previously stored alignment data. For example, the previous alignment which was done here was kind of good, so I just loaded this previous alignment data. So you can actually load the alignment data if you trust the previous alignment, and that is usually the practice. You load the alignment, you press standard focus, you bring the specimen to the right height, and you can start obtaining some images by going to the Gatan digital micrograph software. So you choose the TEM imaging mode here, and if I click on view, before I click view, I should ensure that I spread the beam such that the screen is completely illuminated, and then I can lift the screen and click on view here. So I can actually see that the gold thin film, which is the standard cross grating sample, the image is captured on the CMOS camera. This is a Gatan Rio 16 camera. I can simply capture here. You can run this in situ mode. You can start recording movies and so on. But what we'll do now is we will do the basic operations of aberration correction. So we'll understand how the software functions and what is done to get reasonably good aberration correction and how to obtain high resolution images on this microscope. So to run the aberration correction, you go to this ATCore correction software, you switch this on. Fortunately, everything is now automated through the program, and you can see that there are various lenses. Like shown a little while ago on the description of the position of the aberration corrector, you have several coils here. you have the hexapole lens, you have the hexapole 1,1, hexapole 2,1, 2,2, and so on. And you have the transfer lens, you have the quadrupole. Essentially, what the software does is by setting different values to the hexapole, the transfer lens, and the quadrupole lenses, you are sort of creating a negative CS kind of a condition, and the objective lens already has some positive CS value, and by compensating for this, you are trying to obtain the ideal contrast transfer function here. So the whole process of obtaining the image correction or compensating for the aberrations through this kind of a program relies on the idea that when I record the diffractograms, I'm kind of recording the faceplate information here, and by tilting the electron beam at different tilt angles. So if I go to this measurement here, there is something called as, by obtaining a tableau, this is actually called a Zemlin tableau, by tilting the electron beam. So imagine if this is the electron beam, if it is illuminating paraxially, I can tilt it through an angle of 15 milliradians or 20 milliradians, and I tilt it at various orientations. And while this is being done, we know that aberration is a function of the convergence angle, and based on the angle that you're tilting, you're recording the diffractograms, and by mathematically calculating how the aberrations are actually changing my diffractogram, I can compensate for the lens currents and start correcting the aberrations. So the simple step that we usually do for aberration correction is, before I start anything here, I do the standard alignments that are done, that is correcting for the condenser stigmation, and there is something called as corrector coarse stigmation correction. So we will see what is done here, and then we will come back to the software. So I'll now go on to the Cytex software here, and let me bring an area of this sort. Typically, the manufacturer settings are that you go to a magnification of around 300,000x or 400,000x. The first step that you do is correcting for the condenser stigmatism. So I just click on the condenser stigmation here, and I compensate for the shape of this beam close to the crossover point. I should see that on either side of the crossover, this is nearly symmetric. It's sort of the best case scenario. And then I can go to the digital micrograph software, and let me lift the screen, and let us check by looking at the fast Fourier transform how the state of the stigmation here is. So if I So to start with, we've done the condenser stigmation and coarse corrector stigmation now. As you can see, if I bring this to the right height, the diffractogram here becomes sort of an oval shaped, and this is due to the astigmatism. Let me correct this coarsely with this coil and make it as symmetric as possible. You can see that it's becoming more and more circular now, and I'll go to the zero focus and go on. So this is now in an under focus condition, and let me go to slightly over focus condition and see that when I go over focus, the major axis of this diffractogram is changed slightly horizontally. This is still with So being nearly in this condition and clicking on standard focus and bringing the height exactly to the right focus, which is approximately this sort of a condition, is a good starting point to run the corrector software. So when I start the corrector software, what I do is I start with correction of C1A1, which is actually compensating for the beam shift and the defocus value. So if I click on this button here, start C1A1, I can see that, so please ensure that you stop view in the camera software before you start in the corrector software. So when I click on start C1A1, either by pressing this or here, I'm now recording series of diffractograms, and usually there is a confidence value, and you can see that the C1 that is set here, half of the optimum range is around minus 140.6, and the A1 is typically around 1 or less than 1 nanometer. So I can let this run for a couple of iterations, and I can press on this A1 and let us see how it corrects. It is consistently within 1 nanometer range, and the focus is more or less lower than this minus 140 nanometers, so you're almost within the appropriate range. After correcting for the two-fold astigmatism and focus by starting C1A1, I go to Tableau here. A good practice is to start with fast Tableau with an outer tilt range of 15 milliradians. There's no hard and fast rule, but to start with around 15 mrad, it is quite good, and you can start obtaining the Tableau, and you can see that there is some coma here. So based on whatever the software suggests here on the confidence values, please bear in mind that all of these can sometimes be very accurate, or sometimes they can be misleading as well. So it doesn't harm in running the same thing a couple of times to ensure that what you've actually gotten is more or less accurate before you start accepting the values. So we see that both the times the A2, B2 and C3 and S3 are having some kind of an error. So let us accept this, but what I'll do is with a 15 milliradian Tableau tilt and the higher order astigmatisms, I'll not correct now. I'll only start with correcting A2 and B2 here. Let me accept this, and let us correct with A2 and B2, and let me start C1A1 once again, and iteratively we have to keep repeating this. So I can see that this induced quite some change already. So let me correct for two-fold astigmatism. So initially it was in this elongated shape, and now it is somewhat better. It is less than 2 nanometers. And after this, let me start the Tableau again. So the confidence range is 20 nanometers, and the measured value, which is out of the confidence range by about 18 and 30 nanometers for A2 and B2 is shown here. But for a 15 milliradian tilt, if I look at the face plate here, I already have a correction for 16 milliradian in the face plate here. So this is already sort of acceptable. But let me go to a slightly fresh area, which is having more of these amorphous regions. And this is a sort of a good region. And let me start correction once again here. So and I've started the tableau again. I do not see any distortion here, so I think this is in an acceptable range now. And I will accept these values for now. I'll not change any A2 or B2 right away, but instead I'll do a tableau with standard 23 milliradian tilt. And let me start here again. When I do in standard mode, in fast it only got 8 acquisitions at 8 different tilts, but here it does it more. There are about 12 such different orientations now. And you get 4 more inside. So let me accept this. And with the higher tilt angle, let me now correct for the lower order stigmatism first, which is A2, B2. And then let me check for twofold astigmatism again. The twofold astigmatism has not changed much, and I'll start tableau again. So in this condition, it is only having an issue with B2 and S3. I'll also check for C3 at the end. So let me first correct for S3 and B2 and then see what my value for C3 is. So let me correct for S3 and B2 and let me start this. So the procedure is simple. You start with correcting for C1, A1, which is twofold astigmatism and defocus. And then you start with the tableau. And once you correct for these values, so I have to correct for the lower order stigmatism first, which is A2, B2 is again A3 plus S3. So once you iteratively select for which values of astigmatisms depending on C1, A1, A2, B2 and so on, you start compensating. There is actually never an end to this, and depending on your experimental requirements, what I noticed is after iteratively changing each of these coefficients and by compensating for these values, I achieved a state of something like this. The faceplate here looks fine. More than this, with various tilts, I noticed that the shape of the diffractograms is more or less symmetric in all these tilt angles. So with this, I think this is a good enough condition for me. It is an acceptable state of correction. So I save this file now, and I can use this for any future starting point to actually image. And I will also go to the microscope alignment panel here, and I will save this as well with today's date. So once this is saved, I'm already in a good enough condition, and I can go to my area of interest. As you can see in this digital micrograph software, I can, for example, go to any of these gold fringes, and as you can see at the right focus, I barely see any contrast. So I just apply slight under focus and let me capture the image. So here you have your gold sample after you've done aberration correction. So this is a simple workflow for how to run your aberration corrector and get meaningful high resolution information from the TEM. So all the best, and hopefully you'll use this. One important thing that you need to bear in mind is you can never reach an ideal condition for the state of correction. You should be very wise in choosing what is appropriate for the requirement of your experiment and the specimen you're seeing. For example, in these gold fringes that we see now, you can already obtain a resolution of approximately around 0.7 angstrom with the current state of correction, and that is already good enough for most of the inorganic materials. So with this, I'd like to end this session on demonstration on image corrected TEM.